Alrighty, y'all. Today we're taking a look at question 6 for homework 5. And for this one, we're trying to find the change in current in the wire at a specific instant, right? So that's our di dt. This one's a bit of a doozy, but I'm going to do my best, and don't say I didn't warn you, right? So we're going to start by looking at our work from question 5 and just kind of working backwards, right? As we have our EMF is given as our 4 volts, right? But we know that our EMF is our flux dt, right? Cool, pretty straightforward. We got our magnetic flux already. Lovely, right? In our last problem, though, we used a different version of this equation. Our flux equals our BA cosine theta, right? And we differentiated with respect to time and then plugged in and all that jazz. We unfortunately can't do that this time, right? Because this equation here, this one down here, is simplified based on the assumption that our magnetic field doesn't change with area. Doesn't change at anywhere in this area. But since our magnetic field is different along this line as it is to along this line or over here, right? It's different throughout because it's at different radii, all this stuff. Since our magnetic field changes, we can't use this equation anymore, right? So I'm going to set this one off to the side, right? We have to go back to our definition for magnetic flux that's given in the textbook, right? Our magnetic flux is going to be our integral of our B dot dA, right? So this is the same as the definition for our electric flux from before, all that jazz, right? It's just the vector dotted with the area, right? And since we just care about the magnitude, I'm just going to simplify this, right? Since it's a dot product, we can make it BA, oops, sorry. Right, we're integrating, so B dA cosine theta, right? Lovely, great. So now I can go back up. Our theta, right, let's figure out that theta real quick, right? We have our current going to the right. So based on our right-hand rule, our current's kind of looping out and around like that. So when it's going through the center of the rectangle, it's just going to be going straight down, right? So it's going straight down. It's going to be kind of vertical, I guess, coming out, going into the page. And that's also the same direction as our area vector. So it's going to be cosine of 0 or 1, which just means we can ignore that. Lovely. Simplifying things further, right? Integral B dA. I don't know who is taking Calc 3 yet, but when you're integrating over dA, that's when you break it up into a double integrated integral, right? And it's not as scary as it looks. You have b and dx, right, which is going to be just our x here. I'm going to say that. And I'm going to do the second one. I'm going to call it dr, right? Because it's going to end up being like this distance, which is going to help with our distance between from our wire to our where we're going, right? The distance from the wire. And so our r, right? So our x, say we're just starting in this corner, right? It's going to go from 0 to 3, right? Our 3 meters, x just goes from 0 to 3. Lovely, great. R is going to go from 0.5 to 1, right? Out here we have our 0.5 plus 0.5, 1. So it's going to be 0.5 to 1. Lovely, great. We're getting even closer. But how do we just integrate B with respect to R? Well, we can't right now, but the fun part is we have an equation for B, right? We have our magnetic field as caused by a wire based on, as a function of the current and how far away it is from the wire, right? So we move back over here. I'm just going to move everything. Our integral from 0.5 to 1, integral from 0 to 3 of our equation for B. You know it very well, our mu naught times I over 2 pi r, right? So we can plug that in over here. Mu naught I over 2 pi r, right? And we had it dx dr. Lovely, brilliant, good times, right? So now we just integrate real quick with respect to x, right? So the way you solve a double integral is you just take the inside bit first, solve this as if it was a normal integral from 0 to 3 of mu naught I over 2 pi r dx. That's all we're solving for right now. There's no x's in there. And like we said, nothing's going to change with respect to x. Our only change is really going to be over the y direction, right? Because if I have this magnetic field here, the magnetic field across that line, if I'm integrating over that line, it's going to be the same if I integrate over this line or this line. But the problem was it wasn't going to be the same if I integrated over this line or over this line, right? So all we're going to do, right, it's independent of our x. So when we integrate, all right, it's just going to be mu naught I over 2 pi r times x evaluated between our bounds, right, equals mu naught I times 3 over 2 pi r minus everything times 0. It's just going to go to 0, right? Now we plug this back in and take the integral with respect to r. Right? So we're integrating from 0.5 to 1 of mu naught, or I'll just say 3 mu naught I over 2 pi r dr. Now this looks pretty confusing, but most of it's just going to be constants that we can pull out of our integral, right? So 3 is a constant, obviously. Mu naught's a constant. 2 is a constant. Pi constant, obviously. I isn't going to be constant, but it is going to be constant with respect to r. Like, no matter what the radius is that we're looking at, it's going to have the same current that we're looking at. So we can pull that out of our integral because our integral is with respect to r. All right, so that's all that's going to be is 3 mu naught I over 2 pi integral from 0.5 to 1 of 1 over r dr. That's a much easier integral to solve because that's just going to be ln of r evaluated from, again, 0.5 to 1. Cool. So now we get all of this, and we get that our flux, our magnetic flux, is just going to be equal to 3 mu naught I. Actually, I'm going to pull that I out real quick. All right, it's going to be I times 3 mu naught over 2 pi times ln of 1 minus ln of 0.5. All right. Home stretch almost there, right? Ln of 1 is just 0, right? So one more time, just simplifying it real quick. I 3 mu naught over 2 pi times the negative ln of 0.5, right? Cool, lovely, great. Now, we don't have our magnetic flux. We don't have that as just a value. We have that. We go all the way back up here. We have our magnetic flux differentiated with respect to dt, all right? So if we now take the derivative of both sides with respect to time, right, that's going to give us our dflux dt, right? Our nothing over here, this is all just constants. These are all just numbers you can punch into a calculator and find. The only thing that's going to change with respect to time is our current, right? So that's going to be our di dt times this whole monstrosity over here, negative 3 mu naught ln of 0.5 over 2 pi, And remember, if we still remember what's going on at this point, we're looking for the rate of change of the current in the wire. We're looking for this di dt. And we now suddenly have an equation where we know our d flux dt, right? That was just 4 from before. We know all of this because all of this is just a constant. And now we can just solve this one equation, one unknown, for di dt. Right? So really all it's going to be is 4 over that monstrosity, which I'll just rewrite one last time, u naught ln 0.5 all over 2 pi. That's going to give us our di dt. Okay, if you finally evaluate all of that out, it's going to give you an insane looking number. Here's something times 10 to the 6. I think you have to round or something. I don't know. I think my final answer that I got, punching all of this into a calculator, all right, simplifying with our mu naught, divide by 2 pi, all that jazz, I got 9.78 times 10 to the 6, which seems insane, but Kudu marked it as correct. So there you go. And take about, we're finally done, right? Brought in a little too much calculus for my liking. All right. Well, I hope you found this video helpful, as slightly chaotic as it seemed to be. Let me know if you have any more questions on this problem or any other problems that you want me to explain, and I will do my best to try to explain them, because I guess Sydney explains stuff.